Welcome to Breadboarding. In the previous video, we managed to get our 386 processor here and all the bus control logic all wired up and did some initial testing. However, a few issues that I noticed that didn't look quite right, and so I've been investigating that, and I'm just going to update you on a couple of the fixes and going through the test results. This is video 16 in the 386 Breadboard PC series, and in this video we're just going to be finishing off the bus control logic with a few fixes and completing the tests. In the previous video we were looking at the timings for the 32-bit accesses. So in the original COMPAQ DeskPro 386 this was 3 cycles long. You can see here with the orange bit the ready only went low actually after the second cycle here. But in fact, with us, we're actually tying this low all the time. So in fact, you might actually expect this to be 2 cycles rather than 3 cycles. So we'll check that in a little bit, but that will be the reason why. And because we haven't wired up the 32-bit memory board yet, then the signals doing all that sort of stuff don't exist at the moment. And the 16-bit memory accesses, you can see here that it was actually reading 2 16-bit words and were 6 cycles each, a total of 12 cycles. And then over here we've got reading 4 bytes in 8-bit chunks, and each of the 8-bit reads was taking 12 cycles for a total of 48 cycles. So really we can see here that the 32-bit reads are twice as fast as the 16-bit, and the 16-bit reads are twice as fast as the 8-bit reads. So if you just have a look at the tests that we were doing previously, to do the test, we had a 32-bit RAM access using this test program here, which should basically count up from 000 to 64,000 values. Then we had the simpler test, so this was basically just jumping back 4 bytes. And in fact, when I was doing the testing here, I realised that in fact, for the 8-bit ones, it wasn't reading the offset here. This is a -4 byte offset. In fact, it was rereading EB as the offset, which actually gives us a 20-byte jump back. So in fact, the 8-bit only reads this one value, but it still works. It's just that the change in the address here will be -20 bytes every time rather than -4 bytes. And I've also added another test here. So this is actually testing the 32-bit mode, but with this simple jump back program here, jump back 4 bytes. And the reason why I'm doing that is just to provide a comparison. So just to remind ourselves of the 32-bit test. So this was the code. We basically set CX to be FFFF, and then we repeatedly load the byte starting at 0 until such time as our loop has finished. And I thought it'd be interesting just to see how many cycles this would expect it to be, because when I was actually looking at the output, it wasn't sort of reading byte every 2 clock cycles like I might have expected from the timing diagram. And in fact, the explanation here, when we look at the number of clock cycles needed for each instruction, when we look at the loop here, we can see that we have 6 cycles for every read of every byte. So if we are reading 4 bytes, for example, which is where we see the address only changes every 4 bytes. So in fact, we expect 24 cycles to read 4 bytes, and then the address would then change. So in fact, when we look at the trace, so this is the 32-bit test CPU 6, so this was the 4 bytes of test program. You can see that in fact down here, the clock cycles at the bottom here. In fact, the reading of the code, because we can read in the 4 bytes all in one 32-bit read, it actually only takes 2 clock cycles. And again, the reason here is that the ready signal is wired low, therefore it'll actually take just 2 clock cycles and not 3. And over here we can see that with the markers here, where we have the first read to 0000, last read to 0000, and then the next read then goes on to byte number 4. So in fact, if we count the number of cycles here, you can see up here we've got 24 cycles. So for 4 bytes, 24 cycles, so that is 6 cycles per read. So although the reading of the code actually is much faster, because of the clock cycles required per instruction, then in fact our test is going to require 6 cycles to read each byte. So that was our 4-byte test program. Now if we look at our much simpler test program, so this is just saying jump backwards minus 4 bytes. And so what this will do is keep executing the same code, but we'd expect the address to reduce by 4 bytes every iteration. So just repeating this test with our 32-bit configuration. So if you just look at the number of cycles for that test, so it's much simpler. EBFA says jump back to this point and then another 4 bytes earlier, so we get the address decreasing by 4 bytes every time. You can see from the number of cycles here we'd expect to be 7 plus M. Now it's not entirely clear from the definition of M exactly what that should be, whether it should be 1 or 2. And in fact, when I was looking at this, I was observing 9 cycles for the 32-bit, so it's not completely clear. If anyone knows better, please comment below. But I did look into this and it wasn't immediately obvious whether it should be 1 or 2. And if you actually look at the 32-bit test, we can see that in fact that the jump going from FFE4 and then the next one is FFE0, that in fact if we count the number of cycles here, we can see up here it's actually 9 cycles. So 32-bit access takes 9 cycles to do this jump back. Now when we come to the 16-bit and 8-bit accesses, the COMPAQ DeskPro documentation has this table in it. So if we just look at this, for a 16-bit memory read, standard wait states we'd expect to have 6 clock cycles needed for the read. And for 8-bit we'd expect 12. And then with no wait state it should be 4, and 8-bit no wait state should be 6. So this is what the documentation tells us what we should expect. Now in the previous video, this is the output from the previous video. When we did the 16-bit, then in fact what this was showing is that for these jumps, that in fact it was actually taking 96 cycles. So 12 cycles per address latch enable. So address latch enable means there's a new address goes out on the bus. So 12 cycles per address latch enable means that it's closer to 8-bit. And then when we looked at the 8-bit version, again, the 8-bit was actually the same. So there wasn't actually any difference between the 8-bit and the 16-bit. And that was what I'd kind of noticed at the end of the previous video. And after a bit of investigation, I managed to get to the bottom of what was causing the problem. And in fact, there is the M16 line. So this is a 16-bit memory access, that the input into this particular PLD, there's a latched output LM16. And because the latched M16 output here was not working, this meant that 16-bit mode was behaving like 8-bit mode. So in fact, I changed the output enable term to be inverted. Now, if you remember a number of videos ago, I did make a point of noting this, and obviously it's come back to bite me. And in fact, the reason for this was that in fact, when I looked into the documentation for this particular chip, that when this is configured in registered mode, then pin 1 and pin 11 are permanently configured to clock and an active low output enable. So my defining output enable as active high had no difference actually on the registered mode. And because this was wired high, then this meant that it wasn't working. So in fact, I've updated the schematic. So you'll see here now, when we look at the schematic here, the output enable now is now active low, and it is now wired to 0 volts. So this chip has been modified and reprogrammed, and that now seems to have fixed the problem. So now when I repeated the 16-bit tests with this fix, you can now see that for our FFF0 and then FFEC and then FFEB, so these are first one, this is the third one, and we can see that in fact now that jump -4 is now taking 24 cycles, so this is 6 cycles per address latch enable here. This is in fact what we'd expect from the table that I showed you from the DeskPro documentation. And then if we look at our tests here, this was this particular one, and then if we change the no wait state to be wired low, so this will say don't put any wait states in here, run it as fast as you can, In fact, with no wait states, we can now see that we've gone from 24 cycles down to 18. Now, in fact, when I measured this, there are some 4 cycles and some 5 cycles. So this is slightly different from what the documentation says, but we can see that with no wait state, it's certainly appearing faster. So for the moment, I'm happy that the no wait state is speeding things up. There seems to be a difference between some of the cycles, which is not a big deal, but perhaps look into it in the future. So then if we look at the 8-bit tests now, one of the other problems I did notice is that I'd assumed that the 16-bit input into the data bus, that it would actually switch between the two, but I realised that in fact, because the address line A0 would be switching between the bytes, and my test dip switches don't allow for that to happen. So in fact, what was happening is it was reading EB for the jump relative, and then it was reading EB for the offset. So in fact, EB as an offset actually is minus 14 hexadecimal or minus 20. So we just expect to see that the jumps going back in the addresses would be larger with the 8-bit, but it would still result in the address lines changing. So now if we have a look at this with the fix, you can see that our address lines are cycling as we would expect. There's a little bit of a blip every now and then because of the change in 20. And then when we go into here, we can see that in fact we have, for each of these jumps, we've actually got 12 cycles per address latch enable. And in fact, it was 96 cycles required between each iteration of the jumps. You can see here, this is the first jump, and then it gets to FFDC. So this is minus 20. And then the next jump there goes to FFC8. So that's, again, that's gone down from D to C and from C to 8. So that is a gap of 20. So this was consistent, the 96 cycles was consistent of what I was seeing in the earlier video for both the 16-bit and the 8-bit. And then if we look at the no wait states, so if we then do this with no wait states, we'd expect this to be faster. And in fact now we can see now that we've gone from 96 cycles down to 34 cycles. And again, the address latch enable cycles here is between 4 and 5 cycles. Now it's slightly different from the COMPAQ documentation that said I think it should be about 6 cycles. But again, it appears to be working okay. And there may be some other issue that I'll look into as and when we've got more of the system working. But as long as we actually run things at the no wait state set to 1, then everything appears to be working as expected. So the bus control logic appears to be working reasonably well now. Now I was going to go on and add the 16-bit EPROM to the project during this video, but it was going to get a little bit long. So what I'm going to do is to break the video now, and in the next video we'll be looking at adding our 16-bit EPROM, which is where the BIOS is going to go. So what we're going to be doing is adding a small board like this with a couple of zero insertion force sockets with the two 32K EPROMs on, and that's going to allow us to do a bit more testing. So if you don't want to miss out on future videos, then please hit subscribe. If you'd like to leave comments below, I do try and get back to you within about 24 hours. If you found the content interesting, please hit like, just helps to make it available to more people on YouTube. Thanks for watching.